Welcome to this video on the Risk and Vulnerability Assessment, or RVA in short, from the Mission C Climate project. RVA is a systematic approach that enables communities and decision makers to understand and address the growing risks posed by climate change. It involves identifying climate-related hazards, assessing who or what is exposed, evaluating the vulnerability of affected systems, and examining existing or potential adaptation responses. Building on the IPCC's risk framework, RVA considers four interrelated dimensions: hazards, exposure, vulnerability, and responses. Together, these provide a comprehensive basis for assessing climate risks in a local context and for informing strategic adaptation planning. Let's briefly break these dimensions down. Hazards are potential climate threats such as floods, droughts, or heatwaves. Exposure refers to the people, systems, and the environment that is harmed by these hazards. Vulnerability reflects how sensitive the exposed people, systems, and environments are, and adaptive capacity is the ability to cope, respond, or recover with climate events. The RVA process is typically structured into 5 steps. Step 1 is analyzing past and present climate impacts. Understanding climate risks begins by looking at climate information from the past. Cities assess historical and recent climate events such as heat waves, floods, or droughts to better understand the hazards they currently face and how these may intensify. This involves gathering data from different expert sectors like meteorological agencies, civil protection, health departments, or infrastructure services, and also interviewing local experts to identify the most relevant climate hazards for the area. Step 2 is the analysis of climate projections and future impacts. Adaptation must also account for future scenarios. Future climate risks will likely intensify existing climate risks and introduce new hazards. Using downscaled climate projections, cities assess potential threats under short, medium, and long-term scenarios. This step focuses on understanding which climate trends may emerge, such as prolonged droughts or more frequent heavy rainfalls, and what their local consequences might be. Step 3 is conducting the indicator-based assessment. Each region has unique conditions and challenges influencing its total vulnerability. Using the Mission C Climate tool, cities can apply a set of indicators to evaluate exposure and sensitivity to climate risks. Workshops with stakeholders, such as city agencies, utility providers, and civil protection, help to identify missing data, contextualize results, and to validate the scoring process. This participatory process ensures that findings are valid for each region and help to generate a shared understanding of where adaptation is most urgent. In the 4th step, it's about investigation of interdependencies with surrounding areas. No city is a closed-loop system by its own. Urban areas depend on surrounding regions, and climate impacts in one area can affect other areas in so-called cascading effects. In this step, cities identify key interconnections and dependencies and engage with neighboring administrations and stakeholders to coordinate joint adaptation strategies that strengthen regional resilience. Step 5 is identifying key adaptation concerns and objectives. Finally, cities prioritize where action is needed the most. This involves reviewing the RVA findings to highlight critical risks, especially those already occurring and projected to be at highest risk to intensify. And it's also about identifying where existing systems or capacities offer entry points for adaptation. Stakeholder dialogues are essential here to set shared adaptation priorities and develop realistic, locally tailored goals for resilience planning. So why should we conduct RVAs in our cities? The answer to that is that climate change is no longer a possibility. It is one of the main challenges in the present and the future. The global average temperature has already risen by 1.1 degrees since pre-industrial times. In Austria, that increase is even greater, with up to 2 degrees on average. And alpine regions like Vorarlberg are among the most affected. The Paris Agreement seeks to limit global warming to well below 2 degrees and pursue efforts to limit it to 1.5 degrees. If current emission trends continue, the 1.5 degree target is at serious risk of being missed, and many scientists believe we are on track for 2.5 degrees or even up to 3 degrees warming without stronger action. Therefore, mitigation is crucial, but so is also adaptation. Climate change already affects public health, infrastructure, ecosystems, and also water security, for example. But the nature and severity of those effects vary by region, making local adaptation strategies essential. So now we will have a closer look at the conducted RVA in Vorarlberg in Western Austria. Compared to the reference period, which is 1961 to 1990, all months from January to August had positive temperature and sunshine deviations recorded. The highest deviation was in June, with a plus of 4.5 degrees. And in total, 30% more sunshine hours were recorded in all these months together. Only in September 2022, a slight negative temperature deviation was observed. But the next month, October, broke a new record and was the warmest in recorded history with a 4.2 degree deviation. And also November and December, especially the second half of December, was extremely warm compared to the reference period. However, to have a broad picture of the climate change, it is necessary to look at a longer time period. The next figure shown presents the already visible global warming in Vorarlberg, with almost every year since the mid of 1980s being warmer than the average, and 16 out of the 17 warmest years in the last century occurred after the year 2000. So you can see that heat is one of the observed climate risks. The increase of dry periods and heat can have many, often interrelated consequences on human health, biodiversity, agriculture, water cycles, energy generation and consumption, as well as the infrastructure. So next, let's look at the annual precipitation expressed in millimeters and its deviation to the reference period. Although there is neither a clear trend of an increase nor of a decrease, heavy rainfall events seem to occur more often. And also for Austria, the decrease in snow days play a crucial role. A recent study investigating ski areas around the world showed that the snow days in the Alps decreased from 218 days per year in 1981 to 187 currently. Less snow in the Alps does not only have consequences for ski tourism, but also results in less meltwater that reaches the valleys in spring. This can lead to fewer habitats for flora and fauna, and in the long run, a decrease in meltwater can also affect hydropower. So far, this is not a problem, as heavy rainfall compensates for the decrease in meltwater, but this one may be kept in mind on the long term. Landslide is another risk in the Alps. By the increases in frequency and intensity of extreme weather events such as heavy rainfall and rapid snowmelt, landslides can be triggered. Furthermore, deforestation and land use change can contribute to soil erosion, further increasing the landslide risk. Due to this presented climate risks, including a fast increase in temperature, as well as an increase in heavy rainfall and droughts, and a decrease in the amount of snow in the alpine regions, ecosystems are also affected. Additionally, climate change can alter seasons or the timing of biological events such as flowering, migration, and reproduction. Since most ecosystems are highly sensitive and synced, a mismatch between the timing of these events can disrupt ecological interdependencies. So, what kind of adaptation measures derive from this RVA? To summarize, the integration of heat-resilient design principles into urban planning and development processes is an important aspect. This includes increasing green spaces and implementing cool roofs and pavements, for example. Strongly connected to heat is also the need for an integrated water management to mitigate the impacts of heat on the one hand side and to reduce flood risks as well. Nature-based solutions, which are having a cooling effect and the ability to absorb water through their surfaces, are an effective adaptation measure against heat and water management. When it comes to the protection against natural hazards, Vorarlberg already has a high level of protection against floods. As a response to the floods in 2005, the flood protection measures were adjusted. However, the implementation of monitoring and early warning systems for such a flood management, as well as the protection of forests, should be included in future adaptation strategies. To summarize, RVA offers a structured approach to assess risks and derive with adaptation measures, reducing the vulnerability of a region. It should help to engage stakeholders and to prevent future damages, leading to higher climate resilience. It helps cities to protect people, infrastructure, and ecosystems against the already occurring climate change. I hope this video helped you understanding the RVA approach. Now that you know more about conducting RVAs in a more general explanation and with a specific case of conducting an RVA in the region Vorarlberg, I hope it helps you in your own risk and vulnerabilities assessment. That is all in this video about RVAs. Please have a look on our other videos with topics related to the Mission C climate project.